This is the third video in our series covering topology at like an advanced undergraduate level. And in previous videos, we motivated the definition of a topology, looked at open and closed sets, and now we're ready to look at functions and more particularly continuous functions and what the correct definition of a continuous function is. But let's recall some basics of functions first. So let's say we've got a function f from x to y, and here x and y are just sets. We don't have a topology on them necessarily. And let's recall that we say that f is injective if whenever f of a equals f of b, we know that a equals b. We say it's surjective or onto if its image is everything. So in other words, for all y in y, the target space or the codomain, there exists an x in x, the domain, such that f of x equals y. And then we say that f is bijective if it's injective and surjective. Let's also recall some notation about how f, the function, interacts with subsets of both the domain and the codomain. So let's say we've got a subset A of the domain x and a subset B of the codomain y. Then we'll use this notation here, f of capital A, to mean the image of A under the map F. And that's just going to be the set of all f of little a as A runs through all A. So like I said, we often say this is the image of the subset A. And then we're also going to need the notion of a pre-image, and that's written as f inverse of b, but it's not the inverse function. That's important. It's the pre-image. So often we're more careful to say the pre-image of b. And that's going to be all x and x that get mapped to b. In other words, f of x is inside of b. So if you need more review on this, I urge you to look at my playlist of proofwriting. It covers a whole class in proofwriting, and I do several videos about sets and functions. Okay, so let's look at a couple of examples. So let's say we've got a function from R to R defined by f of x equals x squared. So I've got a little graph here which we may use during this example. So I'd like to prove that it's not injective first, and that's actually pretty easy, and we can do that with just an observation. Let's notice that, for instance, f of negative 2 equals 4, because negative 2 squared is 4, but that's the same thing as f of 2. But we know that negative 2 is not equal to 2. So that means it doesn't satisfy this rule right here for injectivity, and thus it's not injective. It's also not surjective, and that's because notice that it misses every negative real number. So in other words, f of x is not equal to, for example, negative 1 for all x in R. That's because the square root of negative 1 is not a real number. So now let's look at some examples of images and pre-images, starting with the image of this set containing negative 3, negative 2, negative 1, 0, 1, 2, 3. So all we do here is build a set by applying f to all of these numbers. So notice, let's start with 0. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. But then because squaring wipes out minus signs, we get minus 1 squared is also 1, minus 2 squared is 4, and minus 3 squared is 9. So our image is this set 0, 1, 4, 9. Now let's look at the image of this half open interval from negative 4 to 2. Okay, so we could maybe draw what's going on for that up here. So negative 4 to 2 is in the domain, which is generally the x-axis, so that's going to be this thing right here. So let's say maybe this number over here is negative 4, and let's say maybe this number right here is 2. Notice that my scale is not great here, but that's okay. And let's see, I need an open circle on 2. Okay. So I'm looking for the image of this purple set. But I can do that pretty easily just by transposing this up to this point here on the graph and then transposing it over. And because negative 4 squared is 16, we'll put a 16 there. And then we'll do the same thing here. We'll transpose that up to the graph and then over, but that's obviously going to be the point 4. And then, well, everything in the middle gets graphed in as well. So let's see, let's shade that in. But actually we're missing something, because notice that we get these points right here as well, because these points between 0 and 2 are definitely inside of this interval. So that actually goes all the way down here. And it's going to include that origin as well. Okay, so notice that our image interval is the interval from 0 to 16, and it's closed. Okay, there, we've got that. Now let's look at the pre-image of the set from 1 to 9. So let's maybe reuse this here. Let's get rid of these. Actually, let's start with a whole new graph. Okay, so now we've got our new graph. Now we want the pre-image of the set from 1 to 9, including 1 but not 9. So let's go in the codomain, which is the y-axis. We'll start here with 1, and we'll go up here to 9, making sure we're careful about open and closed circles. And now we'll transpose over to the graph, but we have to go in 2 directions. So transposing this over and down, we'll pretty clearly get the point 1 here, and that's going to have a closed circle. And then this to the right and down, we're going to get the number 3, and then we'll get everything in the middle as well. But then going over to the left, we'll get the maybe mirror image of that. So this is going to be the point 1, and this down here is going to be the point -3. Sorry, that should have been -1. And then everything in the middle as well. So notice the pre-image in this case is really 2 pieces. So we might write this as -3 to -1, including -1 but not -3, union 1 to 3. Again, including 1 but not 3. So that would be a nice example of this pre-image. Okay, so now what about the pre-image of the set from -5 to 0, but not including -5 and not including 0? So notice that this is going to be the pre-image of a set of a bunch of negative numbers. But notice that this function does not land on any negative numbers. So that means the pre-image here is simply the empty set. So that's all the points that get mapped to -5 to 0. That's nothing at all. Okay, so now that we've got this example taken care of, let's look at one more. Okay, so for our next example, let's look at a function g from R2 to R2. And it takes xy, which I'm going to write in vector notation, to the matrix 1, 3, 0, 2 times that vector xy. In other words, it's going to be this vector x plus 3y, 2y. You could think about these as ordered pairs as well, but let's use this notation. And so you can pretty easily check that this is injective and surjective with linear algebra. And you can do that just by checking that this is an invertible matrix. And since this is an invertible matrix, well, our function is invertible. But let's recall that a function being invertible is equivalent to being bijective. So anyway, g is bijective for that reason. And so since it's bijective, we only really need to do an example of the image, because the pre-image in this case is simply the image of the inverse function, which really takes a lot of the trickiness out of finding the pre-image, because we can work with the inverse function itself. Okay, so that being said, let's look at the pre-image of, the image of the following set. I'll call it A, and it'll be everything of the form t and then 2t minus 1 as t runs through all real numbers. So something like that. So let's make a picture of it here, but I think you can notice that this is parametrizing a line. And we can see that the line being parametrized here has a slope of 2 and a y-intercept of -1. So let's maybe go here to -1 and then put something that looks like it has a slope of 2. So maybe that's not perfect, but that'll be good for illustration purposes. Okay, so like I said, this is our point A. And now we need to find g of A. But we can easily find g of A by looking at what g does to an arbitrary point in A. So that's t and then 2t minus 1. So plugging that in for x and y up there, and maybe doing a quick calculation, you'll see that this turns into 7t minus 3, and then 4 times t minus 2. So what that tells us is that our set G of A, in other words, the image of A, is made up of all vectors of this form. So 7t minus 3 and then 4t minus 2 as t runs through all real numbers. Okay, nice. But now let's graph that as well, just, since we graphed A in the first place. And now we can graph this a little bit differently. We can graph this by looking at a point that's on this graph by setting t equal to 0 and then drawing a line that is parallel to the vector 7, 4. That's like the vector equation of a line, if you will, or a parametric equation of a line. Okay, so let's maybe go over here, like I said, to this point -3, 2. Sorry, -3, -2. So -1, 2, 3, -1, 2. Okay, so we go there right there. And then here we'll go to the right 7 units and up 4 units. So let's see, 1, 2, 3, 4, 5, 6, 7. So that's going to be over here. And then up 4, 1, 2, 3, 4. So let's see, that's going to be right around there. And that's going to be our next point. But now we'll just draw a line through both of those. And that'll be all of the points in this set. So that's our image G of A. Okay, so now that we've reviewed a little bit about functions, maybe not a ton, but enough if you're familiar. Again, if you need more review, go look at that other playlist that I mentioned earlier. Now our goal is to find the correct topological notion of continuity. Okay, so let's recall that initially we took the idea of an open interval in the real numbers, which everyone is familiar with from calculus or even a pre-calculus class, and we use that to motivate the properties of open sets. In other words, to motivate the definition of a topology. And the definition of topology really gives us the properties of open sets in a topological setting. Now we'd like to do something similar, but a little bit quicker with continuity. So let's start with a continuous function on the real numbers. And well, I'm going to use the epsilon delta definition of continuity, which is in fact covered in that Intro to Proofs class. Now you would learn it a little bit more carefully in a real analysis class, but all we need is the familiarity that would have been given in that Intro to Proofs class. But like I said before, we've got a playlist for that. Okay, so we've got f from r to r is said to be continuous, and we're just going to say continuous on all of the real numbers for the sake of argument here. So it's going to be said to be continuous if for all a and r and epsilon bigger than 0, we can find delta bigger than 0 such that the absolute value of x minus a being less than delta implies the absolute value of f of x minus f of a is less than epsilon. Okay. So now what I'd like to do is translate these inequalities into something having to do with open intervals, and thus we can push that into the notion of an open set. Okay, so let's see. Notice that this is equivalent to the following inequality relationship. So here we've got x is bigger than a minus delta and smaller than a plus delta. So that's equivalent to that absolute value inequality. And then that's going to imply, well, it's going to be f of x is less than f of a plus delta and bigger than f of a minus delta. Kind of for the same reason as we did up here. But now, it's pretty easy to change these into interval relationships. So observe that this is x is inside of the open interval a minus delta to a plus delta implies f of x is inside of the open interval f of a minus epsilon, f of a plus epsilon. Okay, nice. But now here's the big jump, and that is that this relationship that we have right above is in fact equivalent to a certain pre-image relationship. It's in fact equivalent to the pre-image of f of a minus epsilon to f of a plus epsilon is equal to a minus delta to a plus delta. Now, if you look carefully over here at this definition of the pre-image, you'll see that this line up here is exactly defining that the pre-image of this interval is equal to that interval. But let's recall that open intervals in R, stood ground, if you will, as general open sets, or they kind of played the role towards general open sets. So we want to think about this more like a general open set, and over here we've got a general open set. And that brings us to what is the topological definition of continuity, and that is the following. So if we've got a function f from x to y, and x and y now are considered to be topological spaces. So they're both endowed with topologies. In other words, we have a notion of open sets in x and open sets in y. Okay, so we say this function f is continuous if for any open set v, which is a subset of y, the pre-image of v is a open set in x. Or if instead of working with the word open set, you want to work with the collection of sets which makes the topology, we would do it like this. So if x has a topology T1 and y has a topology T2, for all v, which is an element of T2, we have f inverse of v, or the pre-image of v, is an element of T1. But recall that we would read this as v is open in y, and this as pre-image of v is open in x. So it's really the same thing. Okay, so now I'd like to do an example of showing a function is continuous using this topological definition of continuity. And this is a function that you could show being continuous pretty easily using the epsilon delta definition. And that, again, would be something we would have done in that previous course. Okay, so let's say we've got this function from R to R defined by f of x equals 3x plus 5. And now let's suppose that v, which is a subset of R, is open. And we're taking v to be a subset of the codomain. Both of the R's are the codomain and the domain, so we just have to remember that here we're using v as a subset of the codomain. Okay. So now what we'll do is set u equal to the pre-image of v, and let's recall that under this setup, we want to show that u is open. Okay, so let's recall to show that u is open in the standard topology on R. I should point out that here we're using the standard topology on R. We have to show that we can find a little delta bubble around every point in u that's still contained in u. Okay, so let's start that setup. So let's suppose that we've got a number a inside of u, and, well, let's recall, or let's translate this u is open down here. So we want to find some number delta bigger than 0 such that the interval a minus delta to a plus delta is a subset of u. So in other words, well, that's the definition of openness in the real numbers, like we used in the previous couple of videos. Okay, great. But now let's notice that a being inside of u, well, that's equivalent to saying that a is inside of the pre-image of v, just because that's how we're defining u. But being inside of the pre-image of v means that if we apply our function f to a, we are inside of the set v. But then recall that the set v is open. Okay. But since the set v is open, that means that there exists a number epsilon bigger than 0 such that the interval f of a minus epsilon to f of a plus epsilon is totally contained in v. So it may look a little sketchy here that we're having this there exists an epsilon instead of a for all epsilon. But recall, we're doing something a little bit different here. We're using the topological definition of continuity, and all we've got is that v is an open set. But v is an open set means that there exists a little bubble around f of a that is totally contained in v, and that's what we're using here. Okay, great. So now what I'd like to do is translate this into, well, what it really is based on the definition of the function. So that means that 3a plus 5 minus epsilon, and then 3a plus 5 plus epsilon is a subset of V. But now we're going to find the pre-image of that. So how could we do this? Well, I think maybe the best way to do this is notice that f, in this case, has an inverse. And we could write the inverse function, f inverse of y, as, let's see, it's going to be y minus 5 all over 3. Okay, so, well, that tells us that this pre-image of our 3a plus 5 minus epsilon to 3a plus 5 plus epsilon is equal to what? Well, notice that this function is an increasing function because it's a line with a positive slope, which means if we apply it to an interval, the image is just going to be what we get by applying the inverse function to the first part of the interval, the left-hand endpoint, as well as the right-hand endpoint. Okay, so let's see. Applying y minus 5 over 3 to this left-hand endpoint, I'll let you do the calculation, but it's pretty easy to see that this is a minus epsilon over 3. And likewise, the left-hand endpoint, or sorry, the right-hand endpoint is a plus epsilon over 3. Okay, nice. But notice this. Since we had this interval is contained inside of V, that means that the pre-image of this interval is contained in the pre-image of V, which is equal to U. And that's just by a subset relationship working with pre-images. So that's again something you would have proven in an Intro to Proofs class when you're covering functions. Okay, good. But look, we've done it. We found a little bubble around A. In this case, it has maybe width epsilon over 3 that's totally contained inside of U. But that's exactly what we needed to show that U is open. But showing that U is open, in other words, the pre-image of an open set is open, is exactly what the topological definition of continuity is. So now let's move on. Okay, so let's look at a pretty interesting example. So we've got a function f. It goes from the doubleton 0, 1, in other words, the set containing just 0 and just 1, to the real numbers. And it's essentially the identity function here, but it's really the function that takes 0 to 0 and 1 to 1. It's not exactly the identity function because the domain and the codomain are not the same, but it's what you would call an inclusion. Okay, so now we'll let V be an open set in R. And, well, notice that the continuity here is going to depend on the topology that we put on this set containing 0 and 1. And that shouldn't be too big of a surprise given this version of our definition of continuity. Because, remember, we could have different collections of sets here that form the open sets. Also different collections of sets here forming the open sets in both the domain and the codomain, which means these words open up here depend on context. Okay, so let's maybe look at all of the topologies we can have on 0, 1. So the first one is simply the one that contains the empty set and everything. So that's a well-known, maybe smallest topology, and this occurs for any set, and this is the so-called indiscrete topology, which we saw before. Another topology we could have has the empty set, it has the singleton 0, and it has the everything 0, 1. We always have to have the empty set and everything. Okay, and notice that this satisfies the conditions of a topology. Recall that that is arbitrary unions of open sets are open and finite intersections of open sets are also open. Okay, and then we've got maybe the one that's dual to this, which contains the empty set, the singleton 1, and everything. And then, well, we've got one more, and let's recall that if this one up here, the smallest possible topology, is called the indiscrete topology, the discrete topology, which is kind of like the largest possible topology contains everything. In other words, the collection of open sets is simply all subsets. And so there we've got all subsets. And now we need to work through some cases. So notice that if V is open in R, there are really 4 cases that we need to look at. 0 and 1 are both outside of V. But if those are both outside of V, then the pre-image is the empty set. I guess I should say here that in these boxes I'm putting the pre-images of V. Well, now let's see, is the empty set open? Well, yes, the empty set is always open. So I'll just put check marks here to show that we have an open set, an open pre-image for V in all of these cases. Now let's look at the case when 0 is inside of V, but 1 is not inside of V. So if we take the pre-image, what are we going to get? Well, the pre-image of 0 is pretty clearly going to be the subset containing only 0, just by how our function is defined. Now observe that that is not open in the first one. It's also not open in this third one. And that's because the singleton 0 is not an open set, but it is open in the second one as well as the fourth one. And so that means already this first case, when we have the indiscrete topology, and then this third case, it's impossible for f to be a continuous function. Because in the case that we have, let's see, V being an open set, but it does not contain 1, but it does contain 0, you see that you get a non-open pre-image. Okay, so anyway, let's look at the next one. If 0 is not in V, but 1 is in V. So in this case, the pre-image is pretty clear the singleton 1. And in this case, the first 2 topologies make that not an open set, whereas the last 2 topologies let it be an open set. Okay, now let's look at our last case where 0 and 1 are both inside of V. And notice in that case, the pre-image is 0 and 1. It's everything. But notice that everything is always an open set, so we've got check marks here as well. Now, recall the notation we're using here. X means the pre-image is not open, and check mark means the pre-image is open. But we've only got one topology that we can put on our set containing 0, 1 that makes this into a continuous function, and it's the discrete topology. So here we have, yes, that does create a continuous function, but no for all of the rest of them. Now let's look at maybe a general version of this result. So here's our general version of that example. So let's let f from x to y be any function. And let's look at this first case if x is the discrete topology and y is any topology. But being the discrete topology means that every set is an open set. Every subset of x is an open set. Recall that was the definition of the discrete topology that we had before. Okay, so now we can prove that f is continuous. So let's let V be a subset of Y, be an open set, and note that the pre-image of V is open, and that's because everything is. And everything is because, again, we're in the discrete topology in the domain. So what that tells us is that f is continuous. Oh, but that's cool. That means if we put the discrete topology on the domain, every function is a continuous function. Now, that may seem good because continuity is a nice, maybe, thing for a function to be, but that being said, this almost doesn't allow you to study continuous functions very well because it means that there's no restriction to continuity. So, in other words, the discrete topology is almost sometimes a little bit too forgiving, if you will. Okay, so now let's look at this second case, maybe dual to the first case, that x is any topology, but y is the indiscrete topology. So let's let V be a subset of y, and it is open. But let's note in this case then that means that V is equal to the empty set or V is equal to everything. And that's because in the discrete topology, or sorry, the indiscrete topology, the only open sets are the empty set and everything. So if we've got an open set in the codomain, it's got to be one of those two. But now let's notice that the pre-image of the empty set is the empty set. I think that's pretty clear. And the pre-image of everything, y, is going to be x. I think that that's also pretty clear. But notice that both of these are open. And that's because, well, we don't know anything about the topology on the domain, but we do know that the empty set and the entire set are always open sets. That was one of the parts of the definition of a topology. But in this case, we get that f is continuous. So notice we've got this kind of nice pair of results here. If the domain has the discrete topology, every function is continuous. If the codomain has the indiscrete topology, every function is continuous. Now let's look at another nice result. So here's a nice result. So let's suppose that x is the union of a and b, where a and b are both subsets of x and they're both open subsets of x. And then let's also suppose that we've got a function f from a to y and a function g from b to y, and they're both continuous functions. And they satisfy this rule that f of x equals g of x if x is on the intersection of a and b. Then we want to glue these functions together to a function on the whole domain and show that that's continuous. And we'll do that as follows. We've got this function h from x to y defined by h of little x. Well, it's little f of x, or f of little x if x is in A, and it's g of x if x is in B. Like I said, we want to show that that's continuous. And we're going to motivate our proof here by drawing a little bit of a picture. Now, a picture is not a proof, but it can definitely motivate a proof. And, well, here's a nice anecdote. Well, I went for help on a topology homework when I was in grad school. And the professor asked what I might want to study. Like, do I want to study analysis, algebra, something else? And I was like, well, I really like this class. Maybe I'll study topology. And then he was like, no, you don't draw enough pictures. You're going to study algebra. And, well, I didn't really believe him at the time, but he turned out to be right. So even though it's not in my nature to draw a lot of pictures, I just like pushing symbols around, we will try to draw a lot of pictures when appropriate. Okay, so anyway, let's say that we've got our entire set here x, and this box is our entire set x. And notice that A and B union to x. So let's color code that. Let's say we've got this maybe wavy line right here, and everything to the right of that wavy line is our B. And then we've got this wavy line right here, and everything to the left of that wavy line is A. So most definitely A union B equals X, but then we've got some sort of overlap there. And now let's maybe draw a picture of Y as well. Now notice that our function may not be onto, so that means we may not shade in everything over here. So let's say we've got this little bubble right here, and this little bubble right here is f of A. And then we've got this little bubble over here, and this little bubble over here is g of B. And then, well, notice that we need to take an arbitrary open set inside of Y. So let's say our arbitrary open set looks something like this right here. So that's going to be my V. But now notice that spills outside of the image of f and g, but that's really no worry there. The pre-image of that part is the empty set. And so that's going to pre-image over here to something like this. Notice that it definitely includes stuff from only B because of this region right here. It definitely includes stuff from only A because of this region right here. But it also breaks down into two pieces based on this. Notice that this part right here is all f of A. So it's going to have a portion maybe on this side, which is f inverse of A. And then it's going to have a portion on the other side, which goes up to there, which is g inverse of B. And we got pretty messy there, but I think it's okay. And let's observe that, notice that the entire thing that's shaded is H inverse of V, but it looks like it breaks down into the union of those two. So let's maybe summarize that over here. So it looks like H inverse of V is equal to F inverse of V union G inverse of V. Okay, nice. So let's see if we can prove that. And we'll prove this just with a set inclusion argument. So let's suppose that X is inside of H inverse of V, but that's equivalent to saying that H of X is inside of V. And now we're going to break down V a little bit. It's not exactly breaking down V, but let's get it written first. So this means that H of X is inside of V intersected with the image of A under F union V intersected with the image of B under G. And that's because if X is inside of H inverse of V, then we've got to land in this part that is mapped on by one of the functions. We can't land out here. So as long as we land in here, it's going to be inside of this second line that we've got here. Okay, but now notice that that union will break down into an OR statement. So that means that H of X is in V intersected with F of A, or H of X is inside of V intersected with G of B. But let's notice that if it's inside of F of A, then H of X is simply equal to F of X. And that's because, well, we've got this F of X equals G of X on the intersection, and then we've got this definition here of our piecewise function. So in other words, we can swap this here. F of X is inside of V, where like I said, we just swapped H with F. And I got rid of the F of A because it's superfluous now that we're working with our function F. And then we can put or G of X is inside of V. And that's because, well, the same kind of thing here, just with the function G instead of the function F. But now observe, that means, or that's equivalent to, I should say, X being inside of the pre-image of V under F, or X being inside of the pre-image of V under G. But then we can push that OR statement together into this union. But that's essentially all we have to do, because we've got V is open set in Y, and then H inverse of V is, well, notice it's the union of two things that we know to be open sets because both of those are continuous functions, meaning that our function H is indeed a continuous function. Okay, so now I'm going to leave you with some exercises. So here are 4 nice exercises to get you going with this material. So let's start by showing that the function from R to R defined by 2x minus 3 is continuous, using standard topologies on the domain and the codomain, as well as the open set definition, kind of obviously. Now let's show that if F is continuous and that U is an open subset of the domain, that F of U, the image of U, may not be an open set. So that's why we define this continuity in terms of pre-images, not images. And all you have to do is find an example. And actually, an example already occurred in this video if you just find it. Okay, so now let's show that if you've got 2 continuous functions, then their composition is also continuous. And finally, show that we've got another definition of continuity via closed sets. So in other words, a function is continuous if for all closed subsets of the codomain, the pre-image is a closed subset of the domain. And that's a good place to stop.